So, yeah, I welcome all you to the last session of this doubt session for the NPTEL course of Strength of Material, and today's topic will be mostly on. We'll talk about failure theories and buckling of columns. So that is the focus of today's topic, and we will uh, solve some problems also. But before that, we'll have a little recap of what we have done in both. Okay, and then uh, we can see you guys can further solve some more problems based on some textbook. But here we have to have a flavor of what all uh, could be could be there as a problem or could be asked. Okay, so first let's have a recap of failure theories. Okay, so as you have seen in the lecture, so mostly I think has been covered. So like first we have the maximum uh, principal stress, or you can say elastic strain theory. Okay, so these two theories are there, also known as Rankine theory. This is Rankine theory. So you have seen that. Then there is maximum shear stress theory, also the Tresca theory. Okay, then we had maximum strain energy theory, okay. Then we had maximum distortional strain energy theory or distortional energy theory, distortional strain energy theory. And then we had the this one, the maximum octahedral shear stress theory, and also known as von Mises theory. And you have seen that the in the lecture that the distortional energy theory and the octahedral shear theory are nothing but the same. Okay, the way is been different for deriving them, but they are same. Okay, so these theories are there, and why we need failure theories first of all. So the basic question should be why we need failure theories. So basically we need failure theories to define a state of stress beyond which there will be failure, imminent failure. Okay, and we need that boundary or that demarcation, that beyond this state of stress there will be failure. Okay, and so that for designers it will be very nice to always be inside that demarcation in the terms of state of stress, so that we never cross that boundary. Okay, we never cross that boundary, and we always remain at the boundary, inside the boundary, and we will never have failure. Okay, so if I draw the something called yield surface or failure curve, also known as yield surface. So I'll draw the yield surface of two famous theory which professor also has drawn in the lecture. So you have tau here, not tau, it is actually sigma 2, I think is sigma 1. So if you look at Tresca theory, so how does it look? Something like this. This should be parallel. And Okay, so this is the envelope yield surface for Tresca theory. Okay, and similarly we have for von Mises. So in von Mises, how we have von Mises, or I will draw over this only, it will be better. So the von Mises actually passes through these corners, and it's a equation of an ellipse actually, but it passes through these corners. Okay, so that is the von Mises theory. Now the yield surface for von Mises theory. So how we write the Tresca? So I will say this is von Mises and this is Tresca. Okay, so basically generally these theories are defined for 3 dimensions, so I have to have a sigma 3 also, but right now I'm just showing in a plane. Okay, so you have gone through that all, that there is a pi plane, and then on that pi plane is nothing but the debitoric plane. Okay, so and then the other things have been developed from there. Okay, so what we do in Tresca, what we say that the mod of sigma 1 minus sigma 2, or instead of that I will write better in the manner that if sigma 1 is greater than sigma 2 is greater than sigma 3, so we have defined sigma 1, sigma 2, sigma 3 in this manner. So sigma 1 minus sigma 3 by 2 should be less than or equal to tau max. Okay, or this is tau max, so basically I will write sigma y, that is yield, by 2. Okay, so this is my sorry, this is my statement for the Tresca theory, and here what is that for failure to be avoided, okay, I am writing this theory for failure to be avoided. So for failure to be avoided, this quantity sigma 1 minus sigma 3 by 2 should be less than sigma y by 2. Okay, so this is in Tresca theory. Now in von Mises, so we have 1 by 3 of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square power 1 by 2. This is square root here, should be less than or equal to root 2 by 3 sigma y by, yeah, sigma y, that's all, root 2 by 3 sigma y. Okay, so this gives the statement for the von Mises criteria. So again I am writing it for that the failure should not happen. So this quantity on the left side should be lesser than this quantity on the right side for the failure not to happen. So basically if I choose a point, suppose this, so this point comes inside the, if I just talk, yeah, Lokesh has a question. Yeah, yeah, yes, yeah, if sigma 3 is, no, that's right. So how we find basically this quantity is tau max, maximum shear. So how we find maximum shear? We find maximum shear by subtracting maximum principal stress from minimum principal stress. Okay, so it depends what is maximum and minimum, doesn't depend on the intermediate. Yeah, so now if suppose this point, there is a point that is representing a state of stress, point being representation of a state of stress. So suppose I define this one, and this is having some state of stress, say suppose sigma 1 star, sigma 2 star. Okay, now this point being, as we know that this point being inside the envelope of the Tresca, right now I'm talking about Tresca. So this side, this being point being inside the envelope of the Tresca, this hexagonal shape. So what will happen, that this material on which we have applied some state of stress, for which the state at a point is this, will not be subjected to any failure. because it lies inside the yield surface. Okay. How also, if we look in terms of the von Mises, this again lies inside the surface of the inside the surface of the yield surface of the von Mises criteria. Also, this point won't be subjected to any yielding or failure basically. But what happens if this point moves to the point, this means at the surface of the Tresca one? That means now the state of stress has changed to a value that may cause yielding as per the Tresca criteria. So if this point moves to this point, the yielding could happen in that material at that state of stress as per the Tresca criteria, not with the von Mises still, because that point still lies within the yield surface of the von Mises. That what I am trying to tell here, because you have to understand that when the yielding won't happen, only when the point or the state of stress, point being the state of stress, here I am clarifying, point being the state of stress lies within the yield surface of whatever, be it the Tresca, be it the von Mises. Okay, it doesn't matter what theory we are talking about. The point being, if that lies within the envelope of the theory, of that particular theory, then it is not undergoing any yielding. Okay. Okay, so this was discussed basically in the lecture, and then you have seen certain problems in which bending will be also accompanied with the torsion and those things. So we'll solve a problem based on that today. Okay, so we'll discuss that in the problem itself. Now comes to the buckling part. So buckling, I'll just try to give a little recap of what is there. So first of all, buckling is a stability phenomena. Okay. Okay, buckling is basically a stability phenomena. Okay, and whether a body, then how buckling happens, what we need for buckling, compressive stresses or strain. Okay, we need compressive stress or compressive strain to have buckling. Okay, now it doesn't matter even whether it is column or a beam or some beam column member, it doesn't matter. As soon as there is a compression, buckling is possible. Okay, so there are different types of buckling happening in column is different, then buckling happening in beam. So the top flange of the beam also subjected to the buckling, which professor has also touched upon in the lecture. That is called lateral torsional buckling. There is called something called LTB, which happens in the beam. Then there is the shear buckling, which happens in the web of the beam also. In steel girders, what happens, the steel girders mostly take the shear, as we have studied, we have seen that in beams, when we go further for some higher courses, we understand when we make the beams of I section. So suppose beams are made of these sections like these. So we see that all the bending moment is taken by the flanges. Bending moment is taken by the flanges. However, the shear is taken by the web. So this web takes the shear. Now you know, in state of pure shear, you know that if there is a state of pure shear like this, so there is one diagonal which is in tension and another diagonal which is in compression. Now this compression, the diagonal which is in compression, causes buckling of the web. So there is the web shear buckling. Then there is buckling happens when you have applied a very heavy load on the beam. So the place where very heavy load is applied, there also due to that heavy load, web buckling occurs sometime. Okay, so this is there regarding the buckling. So that has been taught there. Then the way to solve the, so basically buckling is a stability phenomena, and it is governed by the geometry of the governed by the geometry of the body. Okay, whatever is the geometry of the body, that governs the buckling. Okay, so that is there. So now how geometry governs, we'll discuss further how geometry takes charge there. So then you have seen the equations to develop the buckling formulae. Okay, that is called Euler's buckling theory, or you can say Euler buckling formulation. So Euler buckling formulation, you have seen how it has been developed. So the same, so I'll just show in a pictorial form. So suppose there is a column which is hinged here with a roller at this end. So there is a roller at this end. Okay, now you are applying a load P. Okay, so now it gives a particular shape, something like this. Okay, some shape like this. So you say this is the suppose y axis. Okay, and this is your x axis. So same bending, actually this is also bending, but happening in a lateral direction. See, there is a fine line between buckling and bending. It has been a very favorite question in many of the interviews. What is difference between the buckling and bending? So one difference, as I told you, that the stability, that buckling is a stability phenomena. It's not about applying load, and it is like unexpected something which is happening. Buckling, bending is what we are expecting. We are applying a load. What do we do in bending? Suppose we have a beam, we apply a lateral load. Okay, and we expect that to bend like this. Means the displacement happening in the same direction as the application of the load. That is happening in bending. Okay, suppose this is a beam. So I apply a load, so something like this, it bends. So the displacement or the deflection which you are saying delta is in the same direction as the application of the load. But is it the same in the buckling? No. You see that your application of load was this, but the deflection is happening in this direction, perpendicular to it. So that is why it is, first of all, it is a stability phenomena, buckling. Bending is not a stability phenomena, first. Second is that in bending, the displacement happens in the same direction as the application of the load, but that is not happens in buckling. In buckling, your load application in one direction, however the deflections are in the other direction. They are not in same direction as the application of the load. So that is one of the other difference between these two. And then comes the difference of the equation, governing equation which we formulate. Okay, so actually we use the same bending formula only, but what we find that we get ei d square y by dx square plus y is equals to 0 or something. So basically we found that our governing equation comes in this form in case of buckling. Okay, but in case of bending, the governing equations are something different. So we find there e I d square y by dx square is equals to m. There we find like that. But here there is some term, and with that we have, this will keep on changing. This will change. This won't remain same as 0. In different problem, it will come different. Okay, it will have a different value. Okay, so the governing equation here and the governing equation here are different, because this problem is the initial value problem, that is also called IVP, initial value problem, whereas this is the boundary value problem. Okay, so here initial value matters in the buckling problems, whereas it doesn't matter in the boundary conditions matter in the beam bending problems. Okay, so that is in a sense I have tried to tell you what is the difference between the buckling and bending, because there is a very thin line between the two. Okay, now so the Euler has defined this Euler buckling thing, and we have seen in the lectures also how to assume at a distance x, you assume deflection y, and then you write the bending moment there, and then you use the same equation to come up with the value, this value of the governing equation, and from that governing equation you find that uh, from that governing equation you find that the uh, the equation comes in some form of sort of this. Now you need to solve it, so you have you do what, you have a defined solution, so you say okay, the solution for y is something like a cos k. Basically this comes in a form, you say k cos kx plus b sin kx, and then you so use your initial conditions. So basically your initial condition is that the deflection at this in at this point the deflection will be 0, and then at this point in this direction the displacement will be 0. Okay, and then you solve it further to find these values of a and b, and then you find that one of is being 0, a being 0, then you find this, and from there you find a relationship with k. Okay, and finally you find that your PCR, that is the critical load, comes out to be n square pi square ei by L square. Okay, this is the critical buckling load, which we call also defined by Euler, critical buckling load. Critical buckling load. Okay, PCR is critical buckling load, and we have this formula come as n square pi square ei by L square. So you can see that how the geometry terms are taking how the geometry terms are here to make sure that buckling remains a geometric instability phenomena. Okay, now n is something called as mode shape here. Okay, so n is something called as mode shape. So it defines like how many turns it will take. So first mode will have only one curve like this, however the second mode will have something like this, and if you go for a third mode then it will have something like this. So those are things, but as you know, the load which is minimum will be the first one which will be governing. So as you can see that this n is coming in the numerator, so if I keep this n value apart from anything apart from 1, it will always increase the value of the PCR, and therefore we can't go to the second mode. Okay, because we have to for that we have to prevent the buckling in the mode 1 itself to reach to second mode. So basically we use n equal to 1. Okay, that is the first mode. Okay, because for n equal to 2 if I go, so n square becomes 4, and then it is a very high value. So obviously you can't avoid the buckling in the first mode. Okay, so that is why we mostly go with the first mode, or we have to choose a mode which corresponds to the minimum critical load, because at the minimum critical load only it will start buckling. So there is no need to further go for any other mode. So for this we find that PCR is coming out to be pi square ei by L square. Okay, so this is nothing but the critical load only. Okay, now if I need to define the stress from this, if I need to define the critical stress, so because we are mostly interested in stress, we talk about stress a lot. So if we want to define critical stress, so sigma CR, that is critical stress, will be PCR by A. Okay, that is the cross sectional area, okay, of the column in which you are applying the axial load. Okay, so what happens, sigma CR comes as pi square ei by L square into A. Okay, so we have divided it. Now this term I by A, so this term I by is all what you see, that this whole term I by A is nothing but a representation of the geometry. Okay, it doesn't have any other term, only geometric terms are involved. So what we do, we define this I by A as some r, and we call it as radius of gyration. This r is radius of gyration. Okay, so this r becomes radius of gyration, and we can easily replace that there. So we say sigma CR is equals to pi square E, so r square comes up and this becomes L square. So further what we do, we write pi square E and we take r in the denominator, so we write L by r whole square in this manner. Okay, so here we further say this ratio L by R as lambda square, whereas lambda is defined as L by R. So this lambda is known as slenderness ratio. It is known as slenderness ratio. Okay, and here specifically L is also known as effective length. Effective length. So effective length basically is defined as the length uh, 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 the length between the two consecutive change in the movement actually. So what is the definition of effective length? Is the length between the change in the bending moment curve. So wherever the change, the bending moment is taking the change in its sign, the length between those two is known as effective length. Okay, so for a simple case of this with the two hinges at the top and bottom, the effective length remains same as the length. Okay, so here it really doesn't matter because you know the bending moment curve remains same. Okay, so yeah, so we have defined the critical this thing. So lambda is the slenderness ratio. Now in order to judge whether a cross section will buckle or not, there is something we say: higher the slenderness ratio, higher are the chances of buckling. Okay, so higher will be the slenderness ratio, higher will be the chances of the buckling. Correct. So now that is one way, just looking at the slenderness. Then another way is to look at the radius of gyration r. Okay, so if we look at this factor r, so if we say that lower the radius of gyration, so you can see when the slenderness ratio will be higher, when the lambda will be higher, when r will be smaller for a constant value of L. So I can say in another manner that when lower will be the value of radius of gyration, lower the value of radius of gyration, higher the chances of buckling. Okay, that is another one. Then these two we can say. Then there is one more way to say is how radius of gyration is defined. So radius of gyration is defined in terms of I, that is the moment of inertia. Okay, so you can see that for a same cross section area, suppose I take a rectangle. Now the rectangle has two axes in a cross section, IZZ, IYY. So now the cross section area of the rectangular section remains same, A remains same, but the IZZ and IYY have a different values. That means now again there is a relationship between this R and I. So as I have said, for R being lesser, the chances are higher for buckling. That means for the axis about which the I is less will have higher chance. In that direction only it will buckle. So the column will buckle along that direction which has lower moment of inertia. Okay, so the direction where you will have lower moment of inertia, and that direction only it will buckle in column. Okay, so this is something like which is very effective while addressing the problems of buckling, and sometimes it is very important also because in exam you may be given few figures. Okay, one circular cross section, one square cross section, one rectangular cross section, one triangular cross section. Now it is up to you to find out for same length of the cross section which is supposed to buckle first, like that, or what is the order in which it will buckle. So in that you can use these ideas to come up with a way to find out in which cross section it will buckle first for same load applied for same length of the cross section. Okay, not length, the length of the column, not cross section, length of the column. Okay, so that is there. So this is being discussed mostly in column buckling, and which is also very much used or applicable in this course of strength of material. Okay, so let's move to the problem. We'll solve the problem first. One problem on the uh, on the this uh, failure criteria, and then we'll go for buckling problem. So here is one problem. So here it says that a force F, you can see in the figure there is a force F is applied, is necessary to rotate the shaft shown in the figure at uniform speed. So this force F is applied on this handle of the shaft to rotate it in a uniform speed. The crank shaft, this is the crank. So the crank shaft is made of ductile steel whose elastic limit is 207 MPa. So this crank has the elastic limit of 207 MPa both in tension and compression, with E being 207 GPa and nu, that is the Poisson's ratio, being 0.25. Determine the diameter of the shaft using the octahedral shear stress theory and the maximum shear stress theory. Use a factor of safety of N2 and consider the point on the periphery as section A for analysis. So they have already given that you consider this point on the periphery, it's at the outermost this thing, and this point A has been magnified in this manner. So you can see that due to this load, first of all, what is happening due to this load, one thing is that this will be subjected to bending, this point A. Okay, because this is a fixed end for it, kind of, this is a fixed here, or means it is properly what I am trying to say, it is properly restrained at this end. Now you are pulling this handle in this manner. So when you pull this handle this manner, this point A will be also be subjected to a bending. Okay, so suppose this is a straight, so some bending like this. Okay, so something like this, okay, then that is one. But due to the rotation, we are rotating this handle, so there will be also a torque in the crank here, and that torque will cause pure shear. So you can see that the bending is there as well as the shear is there. Okay, but as you know, due to this bending, as I told, this will bend like this. So the bottom fiber or the shaft on the other side will be in tension, however the shaft on this side will be in compression. That is why there is a compressive force shown here. Okay, to show the way in which the shaft will bend upon the application of this load F. Okay, so now we need to find the diameter of the shaft, of this shaft, so that it doesn't fail in the in this way. Okay, so let's solve this one. So first of all, we need to say it's a solid shaft, so let diameter of shaft be d. Okay, so d be the diameter. So now you see, first of all we need to find how much is the torque acting and how much is the bending is coming. Okay, we need to find that. So how to find the bending first of all? So you can see the load is being applied here, and the distance between the point A and this load application is 20 centimeter. So if I need to find the bending moment or the moment at this point, what I need to do, I need to just multiply this force with this distance 20. Okay, so that means the moment MB, I will write bending with MB, will be I think force is 45,000 Newton. Yeah, so it is 45,000 Newton and multiply by 20. 20 is in centimeter, so I'll divide it by 100 to be in meters. So this will come out to be 5, so it will be 9,000 Newton meter, correct? So I can say, or 9 kilonewton meter. Now I will find, this is MB, my bending. Now I will find the torque, how much twisting is happening. So you can see due to this force, about twisting will happen about the center of the shaft. Okay, so what is the distance between the center of the shaft and the point of application of the load? It is 15 centimeter. Okay, so we can find how much is the torque generated or twisting moment. So it will be into 15 by 100. So this comes out to be 40 for 50 into 15. So if anyone can of you can find this value, 7, I think this is the answer, should be in the answer, Newton meter, or 6.75 kilonewton meter. Correct. Thank you. Yeah. So we got the our movement, bending movement, as well as the twisting movement. Now what is the scenario? The scenario is both of you can see in the figure, in this figure here, that both the bending, there is a compression due to bending and there is a pure shear state of stress. So it is like two different state of stresses are there, in the sense that two stresses are combining. So this is a to make it as a combined state of stress. So we need to find the principal stresses, because if we want to apply any theory which we have seen so far, either being maximum principal stress theory, strain theory, or the shear stress theory, or the distortion energy theory, strain energy theory, or the octahedral shear stress theory, whatever theory we want to apply, we always deal with what? We always deal with principal stresses. Why we are so interested in principal stresses? Because for a given state of stress, the principal stresses are invariant, they don't vary. Okay, so for a given state of stress, we always define our theory. That's why we always define our theory in terms of principal stresses, not in terms of sigma xx, sigma yy. Why? Because sigma xx, sigma yy will change as we change the orientation of the coordinate system, but that won't happen with the principal invariants. So what is the principal invariant? Sigma 1 is a principal invariant, sigma 2, sigma 3, these are principal invariant. So that is why our all the theories are being defined in the term of principal invariants. Okay, so here also we need to find the principal invariant. So these two state of stress will make a final state of stress. Okay, so from bending, what we find the bending stress. So from bending we find the bending stress. So sigma by y is mb by izz. Okay, so in this the I will be the I of the cross section here, because it will bend, no? So the bending will be along this axis. If I draw this section like this, so this will be bending about this, and like this upper part will be in compression, below part will be in tension. So because it's a circular cross section, the I remains same. So our I ZZ will be pi d4 by 64. Okay, so sigma becomes, or sigma b I will write to show it as bending. So mb into y by izz, but however because it's a compression, so I'll put a negative sign. Okay, because it's a compressive stress. So sigma b comes out to be minus b is 9 into 10 to power 6. I will directly convert into Newton mm. Okay, and y, so what is y? It's d by 2. Okay, and izz is pi d power 4 by 64. So you see this comes out to be sigma b as minus 32 into 9 into 10 to power 6 by pi d q. Okay, so this is the expression for sigma v. Why there is a negative sign? To show that it is compressive in nature, that's all. Okay, okay, now we find the shear stress due to torsion. So what we will use? We will use our torsion formula which we have studied so far. So tau by r is equals to mt by ip. Ip is the polar moment of inertia. Okay, so we find tau as equals to mt. So mt is our 6, 7. So 6.75 into 10 to the power 6 into r is d by 2 again, divided by ip, that is pi d4 by 32. Okay, ip is pi d4 pi 32, not 64. Okay, so this comes out to be tau is equals to 6.75 into 10 to the power 6 into 16 divided by pi dq. So this is our tau, shear stress. Okay, so we have found sigma b and we have found the value of tau. Okay, so now what we need the value of sigma 1 and sigma 2 and sigma 3. So here sigma 1, for this case sigma 1 and sigma 3 are defined as sigma b, which acts as sigma b. So sigma b by 2 plus minus square root of sigma b by 2 whole square plus tau square. This is the same formula which we were discussing yesterday. So in this manner only we find our sigma b, and yesterday we wrote it wrong, this tau, instead being r theta it will be rz. So yesterday we were doing this tau as being r theta, and that's why we were getting some different value while solving for the equation for the eigenvalue problem. So this tau being not r theta, it will be actually tau rz. Okay, so from the figure also you can confirm. Okay, this plane we are talking. Okay, so the tau value will be tau rz. Okay, okay, so yeah, so now what we have, so now we substitute the value. Okay, so if we want to find sigma 1 will be sigma b by 2, so that is minus 16 into 9 into 10 power 6 by pi d cube plus square root of 16 into 9 into 10 to the power 6 by pi d cube whole square plus this will be 16 into 6.75 into 10 to the power 6 divided by pi d cube whole square. Okay, so sigma 1 being minus 16 into 9 into 10 to the power 6 pi d cube. I will take pi d cube common from the inside, 10 to the power 6 also I will take common. Okay, so 10 to the power 6 will come outside, and then pi d cube also will come outside, and the rest will become square root of 16 into 9 divided, yeah, that's all, 16 into 9 whole square and plus 16 into 6.75 whole square, correct. Rest I have taken common. Now can anyone tell me the value of this part, this much part in the bracket? So we can write it finally minus I will write it as like 1 upon pi d cube into 10 to the power 6. So here I have minus 16 into 9 plus here I will have some value, square root of that. Okay, 180. You have done a square root of that also. Okay, then this part minus 16 into 9, that will be I think 144 and 180, so I think 36. Okay, so 36 into 10 to the power 6 by pi d cube. So that we got sigma 1. Okay, then we will see sigma 3 as yeah, so only the negative sign will come in between. Okay, so it will be minus 16 into 9 into 10 to the power 6 divided by pi d cube minus uh, this part. So this part will be nothing but uh, yeah, so what I'll do, I'll directly write, because I don't need to calculate any other thing. I'll write 1 by pi d cube into 10 power 6. Here I'll write minus 6 into 9, and it will be minus 180. Nothing changes. So it will become 1 by pi d cube into 10 power 6, and this will become 4 and 2 1 3. So there is a negative sign here. So it will become 324 into 324 with a negative sign. So here 3. Okay. Now we have sigma 1 and sigma 3. So first we need to go with the which theory. We have to go to question again. So it says that okay, determine the diameter of the shaft using the octahedral shear stress theory and the maximum shear stress. First we'll do maximum shear stress. Use a factor of safety n equal to n equal to 2. Okay, so we have to use the factor of safety of n equal to 2. So first we'll do maximum shear stress theory. So what it says, sigma 1 minus sigma 3 by 2 should be less than or equal to. Okay, Pius has a question. How can I get the professor's PPT slide? I mean, so okay, so I think that you have to. I rarely think you can get the slides. The only means is to just capture them when you are going through the lecture. You can take snapshots of that. I highly doubt the professor will share the slides. I think that has been asked in the announcement portal earlier. So professor won't share the slides. You can go to the announcement page and check whether this kind of discussion has happened already there or not, and mostly he won't share. So that you have only way is to take the snapshot of the lectures when you go through the videos. Okay, that is the only way. Yeah, so we have sigma y by 2. Okay, yeah, thank you. So now we need to find sigma 1 minus sigma 3 by 2, and because there is a factor of safety involved, so we will multiply with that factor of safety. Okay, so always remember we multiply the factor of safety. Okay, so let's see the formula. So we saw that yesterday what was n, it was like yield value by design value. Okay, we saw that factor of safety is nothing but yield value, ratio of yield value by design value. So when you take this side, where it gets multiplied with the design value. Okay, so always remember to multiply the factor of safety with the correct direction. Okay, so basically you are trying to increase this value. Okay, so yeah, so now you see I think 2 is the factor of safety. Yeah, 2 is the factor of safety. We have sigma 1, we have sigma 3. So 2 into sigma 1 is what? This thing. So I'll just take 1 by pi d cube into 10 to the power 6 outside, and I'll do 36 minus 324. Okay, and this should be divided by 2 also, because I have to take half, and this should be less than or equal to sigma y by 2. Now sigma y is being given. So in question, sigma y, that is the elastic limit, is given as 207. Okay, so 207 by 2. So this cancels out here, and this is given in MPa. That is fine, because we are using Newton mm everywhere. Okay, that is fine, MPa. Okay, so now I need help from your guys. So I need to find this value 10 to the power 6 into, this comes out to be I think 360, yeah, divided by pi, and this goes here 2 and into 207, sorry, 207, and should be less than or equal to d cube. Correct? So yeah, so if you can, yeah, No, there should be a cube root of that. Cube root. (103.5 mm). Okay, this will be in mm. Okay, so we have found using the maximum shear stress theory. Now we'll go to the other one, that is the octahedral shear stress. Okay, so second will be through octahedral shear stress theory. Okay, now I have just written the formulation. So it is 1 by 3 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square should be less than equal to root 2 by 3 sigma. This will be power 1 by 2 sigma y. Okay, okay, so let's find. We know sigma 1 sigma 2 is 0, so we know sigma 1 and sigma 3. Okay, sigma 2 is 0, so this comes out to be then sigma 1 square plus sigma 3 square, sigma 3 square plus sigma 3 minus sigma 1 whole square power 1 by 2 it should be less than equal to root 2 by 3 sigma y. So 1 by 3, okay, so what is common there is the denominator and 10 to power 6 in sigma 1 and sigma 3. So I'll take that out. Okay, I'll take that out. So yeah, I'll take that out. So what I'll do here, I'll say 1 by pi d cube and into 10 power 6, that I am taking out because you can see there is a square as well as a square root, so same will be coming out. Okay, now I will write the terms. So this will be 36 whole square, this will be 324 whole square, and this is sigma 3 minus sigma 1, so it is minus 324 minus 36 whole square. Okay, and that to power 1 by 2, and this should be less than equal to root 2 by 3, and this value is 207. Okay, yeah, so 1 by 3 into 10 power 6 divided by pi, and this value will be here 36 square plus 324 square, and this will be simply 360 square, and that 2 1 by 2, and then this 3 will be multiplied here, root 2 will be here, and 207 will be in the denominator. 207 multiplied 207, correct, and this should be greater than equal to d cube. Now I will request you also, so here it is a little bit cumbersome calculation. You have to first find this quantity, then you have to take a square root of this quantity, then you have to do a different thing. I will delete this 3 will be cancelled out, so I will remove that 3. So if anyone can help me in that. Okay, you have taken the square root, cube root, and here square root also you have taken. Okay, okay. So d being greater than equal to 100, 102, okay, 118.4. Yeah. So d should be greater than this value. Okay. Okay, I think I have forgot to multiply the factor of safety, so you have to multiply a 2 here. Okay, so, okay, just it will be twice. Okay, because there is no square root involved here, so you can say twice of it. This will be twice, so it will be 8 6 1 and 3 2. Okay, so this will be the value of the diameter. Okay, yeah, okay, so that's how we solve the problem for from the two theories, and basically we design it, mostly time we use them to design the various components. Okay, okay, now let's come to the another problem which is from the buckling of the column, as we have discussed here. So in this problem, so let's first have a read of the problem. So a viewing platform in a wild animal park is supported by a row of aluminum pipes columns having length of 3.2 meter and the outer diameter of this. So you can see that there is a column which is supporting this cantilever part of the viewing platform, and there is a row of columns. There are different columns in this direction. Okay, in this direction. So there are many columns there. The base of the columns are set in the concrete footing, and so basically the base of the column you can see here is being set in a concrete footing. Okay, there is a concrete footing here. So that means, what you assume, if I say there is a base of the column, or if a beam is being fixed in the wall using well packed concrete, what idea it gives about the support condition there? What do you think? What is the support condition? What kind of support condition you can assume for this, or you can relate that this is the best way to assume a support condition for this kind of setting? Yeah, so it's a fixed support, okay, because it has been embedded in the in this rock with the concrete. Okay, so it is a fixed condition. Okay, so the base of the aluminum for the column are set in concrete footing, and the top of the columns are supported laterally by the platform. So this top here, if you see, so this top here is laterally by the viewing platform. So means it will not move laterally. It is laterally supported. Okay, it is supporting it in the lateral direction. That means it won't move in this direction. Okay, but then what you can think of the support condition there of the column? It is avoided to move in this direction. Just that only the problem statement says that it is avoiding the motion of the column, this column, in this direction and this direction, that is lateral direction. So what do you think the support condition there at this top end? Is it fixed? Fixed? It is hinged? Is it roller? What do you think? Because it is saying that you can't move in this direction, means the viewing platform is giving a resistance for this column to move in this direction. That's all it is saying. Okay, yeah. Okay, so okay, we'll see how it is. So let's do the solution. So one thing we have established for this column is that this base is being fixed, that is established. And why we are establishing it? Because it is being properly fixed in a concrete footing. Concrete has been poured here in the end, so that it is not able to rotate anywhere. You have seen how concrete acts, no? You might have seen any time in your life, in your either in your engineering time or in your industry time, that we usually test the concrete blocks. You have seen. Okay, so how rigid you feel the concrete block is? It is very difficult to break it. No, that means this gives a feel of or a mechanical equivalence of a fixed support. Okay, now at the top here, where there is a platform also, the question says that the tops of the columns are supported laterally by the platform. That means the platform which is there, it is only resisting or supporting it laterally. Okay, and it is nothing saying anything apart from that. That means the top condition should be something like this. Okay, so now for this, there is no lateral movement allowed for this case. You cannot move this, but you can move in this direction. And as you can imagine, yes, that could happen. If you think of this platform, obviously the platform can go downward, little bit downward it can go before buckling. Okay, so that downward movement is allowed. Okay, there is nothing which is stopping. So as we are studying, these are elastic bodies. Okay, don't consider it as a rigid. If you consider the column as a rigid, it will remain rigid, it won't deflect. Then it is a different, then there won't be any buckling. If you consider the column as rigid, then there won't be any buckling. Why we are solving the problem? We should sleep. Will never happen any buckling. Rock is rigid, considered as rigid. If I make a rock column, it won't buckle, it will just crack. If the load exceeds through a particular value, it will just crack. It will have a failure surface, proper very nicely cracked surface it will create, but it won't buckle. Basically it's so rigid it behaves as a brittle material, correct? So in the same manner, because the top of this column is adjusted with the platform, viewing platform, and it has been said that the viewing platform gives the top of the column a restraint in this direction. It doesn't allow this top to move in the horizontal direction. However, the motion in the vertical direction could be allowed, and that's why, which can be very nicely represented in this form. So actual problem, this is the actual problem, and we have made the actual problem, we have made a mathematical model of out of that actual problem. Now we know what to do, how to do, everything we know. Okay, so we have done this, you guys have done this in the lecture. Okay, so the columns are now further, the columns are being designed to support a compressive load of 100 kilonewton, means for each column the load which is being resisted is 100 kilonewton. Okay, determine the minimum required thickness T of the column if the factor of safety is 3 is required with respect to Euler buckling. Okay, they are talking about Euler buckling only. And for aluminum, use 72 GPa for the modulus elasticity and 40 MPa for the proportional limit. Okay, so E is being given for this and proportional limit given for this thing. Okay, so what we do? So P is the load coming here. Okay, and you know how is the buckled shape of this. So I will draw the buckled shape. So it will be something. I am drawing the center line. Okay, sorry, I will just draw the center line. Something like this. This will be the buckled shape. I have drawn the center line of the column. Okay, and you have found the formula for the for this case of the buckling. So this is the case where you find the equation KL is equals to 10 KL, tan KL. Okay, you find that KL is equals to tangent of KL. I am not going to go in through that because professor has very nicely with the animation has given there, and this is the same derivation. So this is the formulation comes finally after implementing the boundary the initial conditions, we find that, and finally we write the P critical in this case as something like as this 2.046 into pi square EI upon L square. Okay, L square, correct. So this is the P critical we talk about here. Okay, so okay, now P is given to us as 100 kilonewton. Okay, so in the question itself it is given that the column are designed to resist a compressive load of 100 kilonewton, and we are also having a factor of safety of 3. We are having a 3 factor of safety. That means the final load will be what, or something called designed load, PDL, right? So it will be 300, 3 times 100 kilonewton. We are giving a factor of safety, no? So 3 times this thing. That means 300 kilonewton PD. Okay. Okay. So now let's solve the problem. So what is our P critical? We find P critical using this, and how this came you can easily find through the lecture. Okay, so because if I derive the full, it will be very lengthy, and because the derivation only will cover the whole part. So my focus is here to, the biggest focus was to come up with this, because this is very important. If you have been given and I am fair to you, I don't teach in a sense that you just pass this exam, coming exam. My objective is that you be able to understand whatever problem comes to you. Okay, so the important thing is to convert the question into the appropriate boundary condition. That is very important, and then you should know. So if I tell in a very simple manner, you know that here the displacement in both direction x and y will be 0. Okay, you know that. Also you know that the slope, okay, so dy by dx will be 0 here, or in this case it becomes the other way around, dx by dy. Okay, in this way it comes the other way around. So I will write dx by dy, the slope will be 0, and here you know, so I'll define x and y first, so that no doubt. This is suppose y and this is suppose x. Okay, yeah, so yeah, now then it will be dy by dx only. Dy by dx is 0, correct. And the other thing is the deflection here. So here delta y will be 0. That is the lateral restraint from the platform. Okay. So yeah. So what we need to do now? Okay. Most importantly, the cross section is also given. We didn't look. So the cross section is given. It's a hollow. Okay. And the outer diameter d is given. And even the value of the outer diameter is given 100 mm. What has been asked? What is the thickness? Okay, so the thickness has been asked and the outer diameter has been given. Now if I ask you in which direction it will buckle, so you know that for this case the I value or the second moment of area or the moment of inertia is same for all the directions, be it Ix, in this case I xx, yy or izz, whatever I call it, it will be same. So here you means you can't say in which direction basically. Okay, now it depends. So as professor also spoke about one of the example in the lecture, that for figures which are which have same eye. Okay, so for those figures where you don't have a defined, for rectangle there is a defined way, because in rectangle you have I yy lesser than, always if it is a proper rectangle then you will find that Iyy is always lesser than Izz. So when that is there, you already know that it will buckle in Iyy because that is less. But for the figures like this, for a circular cross section or a square cross section where you have I same on all directions, then it depends on other factors, external factors like what is the eccentricity of the load. Suppose this is the center and the loading is applied here with the eccentric load. So what is that eccentricity? That also matters. Then is there any defect, already present defect in the column? If the column has been defect in one direction, it will have a higher chance to buckle in the direction of the defect, where the defect influences the column most. Okay, or it kinds of try to reduce the moment of inertia in whatever direction, the defect, because defect also can cause a reduction. Okay, so we may not able to quantify that reduction or quantify that reduction in the moment of inertia due to defect, but by nature it will deflect, it will buckle in that direction. Okay, so that is there. So but if everything is ideal, if I say everything is ideal, there is no defect, there is no eccentricity, okay, so everything is perfect, then in that case it can buckle in any direction. And even if you apply the maths, so from that maths, the as I told you initially, there is something called n, small n, which is the mode shape. So with mode actually that is actually a mode number, and from that there is a corresponding equation of the shape of the deflected curve or the buckled curve. So that buckled curve could take any shape, also is represented by the proper maths. If you apply the proper maths, you will find out that it could take any shape, means any direction of the buckling. Okay, shape remaining the same as the sine curve or a buckled curve, or maybe mostly of the sine nature, but which way it will buckle could be different. Okay, so we have this. So we say 2 point, so we were substituting the values 046 into pi square E into I by L square. Okay, now we will find one quantity, each quantity one by one. What is E? So E is given to us as 72 GPa for aluminium. Okay, this is 72 GPA. I'll convert it to MPA. I need everything in MPA. 72 into 10 to the power 3 MPA. Correct. Then I. So how I is defined for a section like this? So one thing is this. So here you have T, this is the thickness, and total D is the diameter, is the D, outer diameter is the D, which is given as 100 mm. Okay, so it will be what? 1 by uh, uh, 64 pi d. Basically the formula is pi d cube by d power 4 by 64. So pi will be there, sorry, pi by 64. So outer diameter is 100, so I'll say 100 power 4 minus what is the inner diameter. So inner diameter d inner is what? Capital D by minus 2t. So it will be 100 minus 2t power 4. So it is, I'll keep it as like that. So what we can do also, like we can apply the a minus a square minus b square theorem also, or we can finally open that term and we can solve it, but we'll keep it like this because it is always better. We'll take this cube fourth root, that will be better, so instead of opening it right now. Okay, so that is I. So yeah, and yeah, and L is given as I think 3.2 meters or 25 meters. Yeah, 3.25 meter is the length. So L given is 3.25 meters, that is in 3250 mm. So I am writing everything is in mm. Yeah, so whatever P critical comes, 2.046 into pi square into 722 into 10 power 3 into I. So I is pi by 64 into 10 to 100 power 4 minus 100 minus 2t power 4 divided by L. L is 3250. Now this value, which is a critical value, should be what? Should be always greater than some value. Okay, so this value should be always greater than what? What is the load we are asked to take? The load was 100 kilonewton, and we are asked to have a factor of safety of 3. Okay, so we need to have a factor of safety. So how we define factor of safety? N. We say P critical to our P design. Correct. Here critical is this pre-critical. So we multiply the factor of safety with the design. Okay, so we say this whole thing, or I will write there, this should be less than equal to 300, and here it is kilonewton, so 10 to the power 3. Okay, so this should be this value. So if I need to find the value of that, 10 to the power 4 minus 100 into power 4, so this should be less than equal to 300 into 10 to the power 3 into 3250 and divided by 2.046 into pi cube, and there will be 164 here, pi cube into 72 will be there, into 10 to the power 3 will be there. Yeah, these guys cancel out here. Yeah, now I need help from someone to find this value. I will write here 10 to the power, just right hand side first, 100 minus 2t power 4 should be less than equal to 300 into 3250 into 64 divided by 2.046 into pi cube into 72. So just first find the right hand side, or you find directly this quantity, then not right hand side. 3 okay, I have a negative sign. Okay, I'll change accordingly. 300 into 3250 into 64 divided by 2.046 into pi cube into 72 should be greater than equal to 100 minus 2 to the power. Yeah, so if you can find the value of this, what is this, and then take a fourth root of that also. So I'll keep writing, you just find, I'll keep writing. I'm just writing the form so that others also understand what I'm trying to do. 2.046 into pi cube into 72. I'll do a fourth uh, root, should be given 100 minus 2t. Just check what this value is coming. Anyone is able to find this? Let me check whether I can find this value. So 300 into 3250 into 64 divided by 2.046 divided by uh, divided by pi cube divided by pi cube and divided by 72. Okay, then this should be minus from 100 to the power 4, and then this should be taken power as 1 by 4. LHS is 31.51, but I am getting something different. I am getting this value very close to 100. Let me just check. Yeah, this is that, then yeah, so minus 100 and divided by 2. Yeah, that's correct. LHS is approximately 100. That I am also getting. I am seeing whether we have done any mistake somewhere. That I am checking now. So 3250 goes there and 64 goes there and pi cube E is GPA, so MPA correct, 2.046. Yeah, approximately 99.99 something it is coming. Okay. No, wait, but that's what, so it doesn't serve our purpose. It should not be that much near to 100, because okay, every other units by us is in mm. We are all putting units in mm. 3250 is in mm. This is also in mm. Okay, I think we have used factor of safety correctly. Yeah, that is correct. PCR pi square EA by L square. Okay. We have done a very silly mistake. Sorry, guys. Sorry. Should be a square of 3250. See, it's L square, and I had L only. My mistake. Sorry. So now I think it will be not that wrong. It should not come near to. So wherever you find 3250, you make a square of it. Okay. Wherever you find 3250, make a square of it. Then I think now I think it will be correct. I'll also check. 3250 square, then into 64. Okay, that is divided by 2.046 into pi cube into 72. Correct. Yeah, and that is okay. Then its power will be 1 by 4. Yeah, 86. Correct. Then I'll subtract this. Correct. Yeah, now it's correct. So I found the even answer. So answer is coming. T will come as 6.8243 mm. This is the value of T. Okay. Okay. This is the value of T. So that's how we'll find the answer. Okay, you can do the calculation. I have done calculation myself, and I found that T will come out to be 6.8243 mm. So even you can round off to 6.82 or 6.83, whatever. So that will be the answer. Okay, because it can't have, earlier it was coming very low, so that's not possible. We are because dealing in mm, so all the thickness should come nearly to some 5 mm or 6 mm. So that was my concern. So now it is coming correctly, 6 mm. Okay. Yeah. So we found the 6 mm. Now what we can do, one more thing we can do. So what happens that we have designed it. So let's say what I'll say, because see, in design is very difficult to get a 6.82. So I'll say let take design value of thickness as 7 mm. Okay, because there is a sign. So you can see, so there is a greater than equal to sign here. Okay, you can see that there was a less than equal to sign here, but what I had to do, I had to do this, take this negative quantity on this side. So what I had to do, I had to multiply both sides with a negative sign. So when I multiply both sides with negative sign, obviously the sign will change. So this sign gets changed. Okay, so yeah, then we get what we get, this one. So I am taking more than that. If I am taking thickness more than that, what happens to our eye? Let me just check. So if I take, instead of 6, if I take 7, so what happens to our eye becomes, this quantity becomes, means this quantity becomes more, so this quantity becomes less. 2t, if t is higher, 2t is higher, but 100 minus 2t is lower if t is higher, and this quantity being lower, this quantity being higher. That means if I take more thickness, the I will increase. So let's find I. I is pi by 64. 100 to power 4 minus, I have taken 7. 7 to the 14. That is 86 square. So what this comes? Can anyone tell me? What is this value? Sorry, 4. What square? 4. So 100 power 4 minus 86 power 4, and that 2 multiplied by pi divided by 64. So I am getting this value as 2223618.49481. Okay, some mm4. Correct, this is the value. Now I need to find, I'll check, because I want to check my pre-critical. So pre-critical is what? Pi is 2.046 into pi square ei by L square. Okay, so 2.046 pi square, E is 72 10 to the power 3, I is this value 2223618.49481 divided by L, 3250 whole square. Now if you calculate this quantity should come then the proportional limit, because it should be elastic. The value should be remain elastic. So two point 046 into pi square into 72 into 1000 into 2223618.49481 divided by 3250 whole square. Correct. Okay, which value we have put in which as mm, and that is in E is in GPA, so that is correct, and this is m power 4 m square. Okay, I need to find actually sigma critical. So sigma critical is what? Divided by the cross section area, 046 into pi square ei by L square into A. So whatever quantity I get, I divide by area. What is area? Area is pi by 4 100 square minus 86 square. This is the area, no? Outer circle area minus inner circle area. Correct? Yeah. So we divide it with pi uh, into 100 square 36 square. Yeah, so it is coming, this value is coming 149.658 Newton per mm square or MPa. Correct? So which is way lesser than the sigma critical is way lesser than the proportional limit. What is proportional limit? You can see the proportional limit is 480 MPa. So it is lesser than 480 MPa. It should remain within proportional limit. So that's why I checked this value, whether it is remaining or not. So it is remaining. Okay. So that's how we find the value of the design problem, because it's a basically design problem. So you have been given a load, and then you have been asked that how much will be the value of the diameter you need to find, and for that then you find the and you have to again check for the diameter whether your proportional limit should not be exceeded at any cost. Okay, and it's a thumb rule that it should always remain below the half of the proportional limit. So we have 480, so I would say always it should be below than 240 MPa, the buckling, because it's a very, as I said, it's a stability issue. So a very little perturbation of the system around the P critical value will cause a significant failure. Okay, it will cause a significant failure. So that's why it's a stability issue. So that is why this is a major concern in many of the constructions. Okay, yeah. So anyone having any question, any doubt in this what we solved today? Any doubt in this problem? Yeah. Yeah. Sure. Yeah, sure. Yeah, thank you all you for being here in this journey, and it is very insightful for me also. Like I have also learned from this, because when we do go in research, then we don't get that much time in courses. So this was also a way for me to come back and look everything in a different perspective, and then try to put to you guys so that you be able to solve some of the problems. My motive is not as my life's motive is not to remain till the NPTEL examination, although it should be your motive at right now, but my motive is if you get it pass, then that also, because we should always keep our bar high. So learning should be in that sense. So I think you guys will be somewhere you will be benefited with this, and will try to, and you try to solve problems. Okay, so that will only give you the confidence. I think that is the only way to get good confidence that you can handle then problems. And I wish you all the best for the exam, and I hope you get very good grades in the exam, because you guys have all been very very hardworking in this, because you've been through this for all 12 sessions with me. So I am pretty sure that you guys will be able to handle problems very this thing, and always look for the I would say trick, because always trick will be there. So don't jump the gun initially, just hold on and then look for the trick. Okay, so you should do not miss the trick, because sometimes what we do, even I also sometimes will go in some hurry and will miss the trick. So trick will be there, means sometimes trick will be there. Because and it will be mostly in those questions which you feel, oh, this seems very easy. So it's like just I am sharing my experience. So when we feel, oh, this seems easy, it is some nothing, this some formula putting thing. I personally think nothing will be formula putting. That's my personal view. Okay, so I will always say look for the trick. There will be some small something conceptual thing which will, and always it will be a conceptual thing. It will nothing that will make you to mug up something or this thing. Okay, small formulas like how to find second moment of inertia of a cross section, that is a different story. We should all know that as an engineer. So, but other conceptual things will be asked in a manner that it is expected out of us. So I would say that you guys don't miss that trick and go with that, and manage your time in the exam so that you be able to solve. And if you get some time, because I think it is an objective oriented, so either you need to click the options or you need to put the figures 1 2 3 like that, some integer value you have to put. So my thing will be always try to manage your time in the sense that you are able to review some of the critical questions which you find that you have to review. At least you find the time to review those critical questions so that you solve it with the proper pace. Okay, so you should be able to attempt all and then review some of the important where you think there could have been a mistake or could have been a oversight in some of the values or something. Okay, and yeah, and mostly the question will be, see, it's a mechanics course, so there will be calculations involved. Okay, so when calculation involved, so your calculations, and you don't have a physical calculator, so you have to have a virtual calculator. So you should be able to practice that also. So I have a suggestion that you use your laptop calculator. So when you solve, you use your laptop calculator. I think that will give you uh, better practice to access the virtual calculator. I think that will be there. And thank you very much for joining these sessions and being the part of this wonderful journey. It helped me a lot also. Okay, thanks a lot. Okay. Uh, yeah. Okay. Yeah. Yeah. Yes. 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 Yeah. Yes. 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 Yeah, I tried my best. If I did anywhere wrong, I'm very sorry for you all. If I may not be able to cover your expectations, but I tried my best. Yeah. Yeah. Yes. 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 Yeah. 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 Yeah, when we are discussion, there is no point then in to track the time, because it all matters that how we were able to come to a conclusion, that matters. Yeah. Yeah, sure, sure, sure. Yes, 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 yes. Yeah, sure, sure, sure. Yes, 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 yes. Yeah, yeah, sure, sure. Yeah, 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 yeah. Thank you, thank you, thank you very much, thank you very much. Yeah, thank you for your kind words. Thank you very much. So yeah, so I yeah, thank you, sir. Thank you very much. Yeah, thank you. Yeah, I hope you all guys do very well in exam. So that those things are, because there will be some trick that I know. Always it happens. Even in IIT we see every exam, every quiz, everything. It happens there. So be look. You should look for that. And because I also personally like the physical calculator, but the problem is there is no way we can't change the rule. Even the I wrote my gate with the same virtual calculator. I even didn't get the chance. So before me writing the gate, it was removed, the physical calculator. So but yeah, the only way you can do is you have to live with whatever it is there. So best way is, I would say, because you don't have any other access, if there is any app or something you can download from online which will show you some physical calculator, virtual calculator, then it will be very good. But if you don't, then best is to go with the computer calculator and try to solve with that using your mouse or something, so that you get a practice. Because there the only time you will, what I have felt, will be like, when you formulate in a sheet of paper or something, you will do it quickly, but when you put that figures in calculator and come up with an answer, that takes time. So that is, I think, where a little bit this thing practice is required. Rest, you guys have gone through all lectures and videos, so that will be the technical part of it. But that there you have to do a little bit extra, so that you save a time, and that time will be very important when you review your answers for those questions which you find that they were quite tricky, or there lot of calculation was involved. So if you get time, you can review your answers also. So that would be, I think, will be better for your final exams. Yeah, yeah. Okay, okay, bye. Thank you, thank you, thank you, thank you. Bye, bye, bye. All the best. Thank you. Bye. Yeah.